Back to our cones. Since I don't have any good ones to use, then here's what you need to imagine happening. What we're going to do is we're going to take two cones and we're going to put them tip to tip. And when we slice them, here's how we're going to slice them. We're going to go straight up and down. We are not going to pass through those points on our cones. And by going straight up and down in that fashion, what we end up having happen when we look at that kind of cross section is what we refer to as a hyperbola. A hyperbola, as far as the geometry definition here, set of points where the difference of distances between two fixed points is constant. And again, since it's the difference between distances, we want to make that more convenient than just constant. Let's say it's constant and positive. That makes things just a little bit nicer for us. So notice that there's a lot of similar wording between a hyperbola and an ellipse. The difference between a hyperbola and an ellipse is that we have a difference instead of a sum of distances. You could kind of say that if we took an ellipse like a balloon, blew that sucker up, that ellipse would just kind of explode out, right? And so the vertices on that vertices on the ellipse, kind of like it explodes outward. The vertices stayed the same. Now what's happening is the foci got blown out. So the foci are now blown out, and the way that that ellipse has ended up just kind of blowing out on us is that it's just like... So that's a cute little way of trying to think about things. What we have going on, though, because of the nature of what we're talking about and what we're looking at here, for lack of any better wording, let's call these two interior points here the vertices, the same as we did before. Because this is different from the ellipse, those vertices are now the interior points that we see, while the foci are further away from that center. Notice that what we've got going on here as well is a little bit of something extra that we hadn't seen with any of the other shapes. We now have some asymptotes to deal with as far as this exploding idea. That's things exploding out and away. We're getting that asymptote business happening. In terms of referencing the orientation, our hyperbolas can open to the left and right. Our hyperbolas can open up and down. But what we talk about here, because we've only got one set of points to work with that's nice enough from the vertex to the vertex, because that's outside of our shape rather than inside of our shape, we don't want to refer to that as the major axis. We'll refer to it as a transverse axis. So a slight tweak to the terminology that's being used here, just to try to make sure that things don't get confused. Now, with some differences and some similarities, we want to make sure we don't get confused about things. So, what's different? What's the same? One of the things that's different is the relationship between the A's, B's, and C's. In the hyperbola, B squared is equal to C squared minus A squared. Not the other way around anymore. B squared is equal to C squared minus A squared. So now, it's the C squared that's bigger. We could say that because we changed from the sum of distances to the difference of distances, we have changed the ordering of this relationship. B squared equals, for an ellipse, A squared minus C squared. Because a hyperbola has the difference, this relationship changes so that it's B squared equals C squared minus A squared. The equations. Instead of having an equation where we only have these plus signs showing up between our x stuff and our y stuff, in the hyperbola we have a minus sign in between them. So what we can say about this particular situation is that when the x squared stuff is positive, we open to the left and right. The a squared is always underneath the positive variable. If the y squared stuff is positive, we open up or down, up and down, frankly. And again, the a squared stuff is always underneath the positive variable stuff. We have a center, we have vertices, we have foci. Let's look at those. Bring up that continuing list here. So the center, still not tweaking that at all. The center, 0, 0. The vertices still use the A. The foci still use the C. So at least those things are the same. But because in the hyperbolas, the A stuff is smaller than the C stuff, it's now the vertices are closer to the center and the foci are farther away from the center. But at least thankfully, those are still the same sort of, memory arrangements in my mind. Vertices still using the A, 0, negative A, 0. The foci still using the C, 0, and the negative C, 0. Bring the rest of that list up here. Our asymptotes, we could combine them together and say plus or minus, but that sometimes becomes squirrely when we talk about shifting. So instead, kind of separate them out in the hopes of not making some sort of mistake in the future when we shift things away from a center at the origin. The asymptotes at first in the open left-right situation use a normal y equals something x. What we've got going on here is a b over a. When we do our xy switcheroo, notice what I have written down here. I just literally did the xy switcheroo. That way I don't have to remember a brand new version for what those asymptotes look like. I can create it if I need to get a normal looking line y equals mx plus b. I can get that. But the xy switcheroo certainly gives me a good jumping off place where I don't have to remember as much. The length of the transverse, again, since the transverse is like the major axis, it's not the major axis though, since it's like the major axis, it still has that same length 2a. The eccentricity also still c over a, except for this time the eccentricity is kind of telling us how flattened out our hyperbola branches are going to be. So if we're using the open left, open right version, if we're talking about things that are squished down, or if we're talking about things that are very opened up, the eccentricity is going to give us an indication of that type of thing. XY switcheroo still in place. Vertices, switcheroo. Foci, switcheroo. The asymptotes, like I just mentioned, instead of y equals b over a times x, switcheroo those x's and y's. X equals b over a times y. Just keep it direct to remember that list. Standard sort of equation showing up here, nothing fancy, nothing crazy, just trying to emphasize those relationships. We've got the y squared over 9 minus the x squared over 16 equals 1. The fact that we've got the equals 1, yay. The fact that we've got our positive stuff showing up out front, yay. That just makes things a little nicer looking. The positive stuff is what I'm using to help get my orientation, because my positive stuff is the y stuff. My transverse axis is going to be vertical. That means that my my hyperbolas are going to be opening up and down. In fact, let's go ahead and make that quick comment in there. Don't want somebody to lose sight of that. So, open up and down. The a squared is always underneath the positive variable stuff. So the a squared is going to be the 9, the b squared is going to be the 16, and the relationship here that we have for the hyperbolas is that the b squared is equal to the c squared minus the a squared. That allows us to figure out the C value. Once we have the C value, we can come up with all the list of the characteristics. So our center, unshifted, the origin. Our vertices, because this is vertical, I got to do my XY switcheroo. So instead of A comma 0, it's 0 comma A, 0 comma negative A. My foci, 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 foci. Instead of C comma 0, it's 0 comma C. Instead of C, negative C comma 0, it's 0 comma negative C. Those have to be aligned vertically. Asymptotes. Instead of Y equals, it's X equals. It's B over A to start out with. X equals B over A. I'll put in my B, I'll put in my A, and I get an equation. Yeah, it's not like the ones I'm usually used to. I usually prefer the Y equals. Now, if we're forced to, we can write it this way, Y equals. I'll rearrange that equation, I'll rearrange the other equation, and I've got those more normal looking equations for the asymptotes. Length of the transverse axis, 2 times A, is 2 times 3, which is 6. The eccentricity in this particular case, C over A, gives us 5/3. Once we have other examples of hyperbolas, we can see whether that eccentricity business, do I get bigger for the eccentricity and get flatter, or do I get bigger with the eccentricity and get a wider hyperbola? I would have to look at more examples before I'm able to come up with a comment to that effect. As I promised you before, we're going to do an example here in another few minutes where we have to work through our completing the square steps. Before we do, shifted forms are still working the same way that we've said before. Instead of X, we have parentheses X minus H. Instead of Y, we have parentheses Y minus K. And so the deal here, I wrote out this suggestion as a means of trying to help folks keep on track. I don't want to say keep focused because math joke. The asymptotes. These are new and different. We haven't seen those before with any of our other shapes. So when we do the shifting, my suggestion to you is this, that when you come up with the basic version, whether it's the Y equals B over A X or the X equals B over A Y, once you come up with your unshifted version, replace your X with the X minus H, replace your Y with the Y minus K, and work from there. It's going to be a little bit less of a hassle for us to make sure that we keep track of everything properly if we do that. So I'll show you what that suggestion means for this example here in just a moment. Maybe get through the rest of this stuff here. First of all, the orientation. My X stuff is the positive stuff in this more standardized appearance. So that means that my transverse axis is horizontal. I'm going to be looking at hyperbolas that open to the left and right. My a squared is always associated with that positive variable, so that means my a squared is going to be that denominator of 9, and my b squared is going to have to be that other denominator of 4, and that'll create from my relationship b squared equals c squared minus a squared. My c value, square root of 13. I can list out my unshifted information. My center is the origin. My vertices and my foci are listed out. The asymptotes, in this case, y equals b over ax, y equals negative b over ax. The eccentricity, like with the ellipses, c over a. And so all that stuff is now taken care of, and I'm ready to shift. So back at the top of the screen, with my parentheses x minus 3, I'm going to be shifting right 3. And with my parentheses y plus 1, I'm going to be shifting down 1. So my center will get shifted right 3 and down 1, and will give me the point 3 comma negative 1. For the vertices and the foci, I can take that center and I can add to each of my vertex points and my focus points and come up with the new shifted vertex and focus points. 3 plus 3 is 6. 0 plus negative 1 is negative 1. 3 plus negative 3 is 0. And 0 plus negative 1 is negative 1. Square root of 13 plus 3 is 3 plus the square root of 13. 0 plus negative 1 is negative 1. Negative square root of 13 plus 3 is 3 minus the square root of 13. 0 plus the negative 1 is negative 1. The length of my transverse axis has not changed. My asymptotes do. So going back to that suggestion, y equals 2/3 x needs to be shifted. Instead of the y, I have parentheses y plus 1. Instead of the x, I have parentheses x minus 3. So I'm actually going to go ahead and start from that perspective. Y, nope, not anymore. It's y plus 1. 2/3 x, not an x anymore. It's a parentheses x minus 3. For the other equation, instead of y, we put in the y plus 1. Instead of x, we put in the parentheses x minus 3. And this gives us something that we can work from. We can get our standard y equals mx plus b sort of appearance to these with a little bit of extra manipulation. So in the first case, y equals 2/3 x minus 4. In the second case, y equals negative 2/3 x, and that's, excuse me, not a minus 4, but a minus 7 that was supposed to be. And then for the other equation, we would have a y equals negative 2/3 x plus 5. The eccentricity also does not change because the eccentricity is not based on x and y. It's based solely on the c and a numbers, so that is not changing and would still be that square root of 13 over 3. Now, if you do not follow my suggestion about shifting those asymptotes, it could be very easy for you to make a mistake. First of all, like what we had said originally, I'm listing those asymptotes separately. I'm listing them separately so that when I do shift them, according to my shifting, according to my original equation, instead of x, I have an x minus 3. Instead of a y, I have a y plus 1. When I'm shifting them, I do not somehow accidentally make a mistake. I have each one listed individually. I can come up with each individual equation and have them correctly identified. If I have not split them up and try to do the shifting, I can very easily make a mistake. Use the split up version. And again, my suggestion, instead of the y, put in your shifted, altered version based on your original equation. Instead of the x, put in your parentheses x minus h, whatever that is, right? So if you're using the y minus k and the x minus h that come from your equation, you're going to be more likely to correctly work out those asymptotes. So be careful about that. That's one of the trickier things. In addition to something that I just kind of glossed right by here with this example earlier, the other common mistake is that people misremember the relationship between the a's and b's and c's. For hyperbolas, b squared is equal to c squared minus a squared. You kind of think of it like this maybe. Hyperbola ends in an a. Maybe that'll work for you. Now again, this was just for the shifted version, trying to emphasize how the shifting would affect that list of basic information. And as one last example, let's go through basically what we might say is the worst case scenario, where we would have to do a great deal of work to come up with a shifted version for us to eventually identify all of our characteristics, the orientation, et cetera, et cetera, et cetera. And then take those unshifted lists and then shift them. So this is, again, the worst case scenario of what you might have when you are working through your assignments. The original equation, 16y squared minus x squared plus 2x plus 64y equals, plus 64 equals 0. Because we have to go through the completing the square process, we're going to keep all of the variable stuff together on the left-hand side, and that means that we're going to move the regular old 64 to the right-hand side. When we do this, we're also going to rearrange things in a more useful way. So for our x stuff and our y stuff, we're going to rearrange things so that the y squared stuff and the y is side by side. The x squared stuff and the x stuff side by side with each other. And when we start looking at things, at first, since the y stuff is positive, let's go ahead and work with that and see what comes up. We're going to want to factor out that 16. So this is a little bit of a change to our method of completing the square. We're going to have that 16 that's showing up. We're going to factor that bad boy out to the front, and we're going to need it in a hot minute. But at least for the moment, we're going to look inside that set of parentheses where we've got the y squared plus 4y, and we're going to take that number in between the y squared and the y and divide it by 2 to get a positive 2. We're then going to take that positive 2 and square it in order to get 4. Now the 4 is going to go inside that set of parentheses so that we will be able to rewrite the set of parentheses as a y plus 2 parentheses squared. However, the 16 is out in front of that set of parentheses. So the 16 and the 4 are going to have to be added to the right-hand side by adding on a 16 times 4. We think of it as a distributing issue. 16y squared we already had. 16 times 4y is a 64y. We already had that. But now we've got a 16 times this green 4. That's an extra plus 64 that we didn't have originally. And so we're going to go ahead and put that over here on the right-hand side to keep the balance. That allows us to do our completing the square with the y stuff. And that would end up giving us a 0 on the right-hand side of our equal sign. We can actually now go ahead and take that parentheses y plus 2 and carry that on through for a little ways. With the x stuff, now that x squared has a minus in front of it. So we want to make sure now that we're very careful about keeping track of our minus signs. We're going to factor out that negative, and that means in the parentheses we're now going to have an x squared minus 2x. We're going to go ahead and work through our normal completing the square steps for just a moment, and we'll worry about that negative in just a little bit. So we're taking that negative 2, we're dividing by 2, that gives us a negative 1. We take that negative 1 and square it, and we get a green 1. And so what that means for us is that inside the parentheses, we're going to be adding a green 1. That means that on the right-hand side, we're going to be adding. Let's do a little different color here for emphasis. The negative out in front, and the green 1. Again, if you think of this in terms of distributing, minus x squared, I already had that. Minus a negative is plus 2x, I already had that. Minus a 1, I didn't have that, and so I'm going to have to put in a minus 1 on the right-hand side to balance things out. What that means for us in the set of parentheses is that x would be it would have an x minus 1 parentheses squared, and then over on the right-hand side we get a negative 1. Now this is problematic because we do not want a negative 1, we want a positive 1. So we're going to have to tinker with this even more than just the completing the square. We're going to have to divide everything by negative 1. Or we could also say multiply everything by negative 1. What that will create for us is a negative 16 parentheses y plus 2 parentheses squared. plus parentheses x minus 1 parentheses squared equals positive 1. So now we've got the positive 1. Yay! We do not have denominators that are showing up here, and that's a little strange. We also like to have, well, maybe you do, I certainly do, I like to have my positive stuff showing up first. So I'd like to have this x minus 1 parentheses squared actually showing up at the front of my equation. And officially speaking, underneath of this parentheses x minus 1 parentheses squared, I would have a 1. Then I'll write my y stuff, and with the y stuff, what we also normally would see is the parentheses y plus 2 parentheses squared over top of a number. Now the only way for this to work out is for this 16 to somehow get moved to the denominator, and so I've got to be a little bit tricky with my reciprocal kind of ideas and go ahead and get that down there in the denominator. When I get it down there in the denominator, that means that I'm going to have a fraction 1 over 16 underneath of my y stuff. Now, if you've already looked ahead to the comment that was down here at the bottom of the screen, well, that means that I had already known that that transverse axis was going to work out to be horizontal, so that we would be looking at a hyperbola, that opens left and right. So, again, positive stuff is x. X goes left and right. Our hyperbola opens along the x-axis. It opens left and right. So our transverse axis is horizontal. This also means that our a squared is always connected with our positive variable stuff. So our a squared is a 1. Let's actually bring this up so it's a little bit more convenient for us to do the rest of our work here along the way. So a squared is equal to 1, and that means that the b squared would be the other denominator number, 1/16. If a squared is equal to 1, that means a is equal to 1. If b squared is equal to 1/16, that means b is equal to 1/4. B squared is equal to c squared minus a squared, so that would give us that c squared is going to be 17 over 4. So c is the square root of 17 over 2. Our unshifted center is the origin. Our unshifted vertices are going to be based on our a value, and the a comes first because our orientation is horizontal. So 1, 0, -1, 0. Foci, foci, our c is a square root of 17 over 2. So square root of 17 over 2, 0, and negative square root of 17 over 2, 0. The length of my transverse axis is 2 times a, which is 2 times 1, which is 2. My eccentricity is c over a, and c over a in this particular case will just give me the square root of 17 over 2. My asymptotes would be based on y equals b over a. Well, b over a is going to be just 1/4. So y equals 1/4 x, and y equals negative 1/4 x. And now I can take all of those unshifted pieces of information here and use my shifting information from this equation at the top of the screen that I have created. That shifting would be from the x minus 1, we would shift right 1. From the y plus 2, we would shift down 2. That would give me a center of 1, -2. I can now take that center and add it to my unshifted vertices and foci, and I can come up with the shifted versions, 2, -2 for one vertex, 0, -2 for the other. For the foci, 1 plus root 17 over 2, negative 2, and 1 minus root 17 over 2, comma, negative 2. The length of my transverse axis remains the same. My eccentricity remains the same. My asymptotes are going to get shift based on, well, let me pull that equation back to the top there for the moment. Instead of y, I have y plus 2. I still have the 1/4, but instead of x, I now have an x minus 1. Instead of a y, I have a y plus 2. I keep the negative 1/4, but instead of x, I have an x minus 1. And so this would allow me to, again, if I needed to or wanted to, convert into my normal slope intercept form, and that would give me y equals 1/4 x minus 9/4, and y equals negative 1/4 x, and that would be minus 7/4 for those two asymptotes. Careful with the asymptotes. Again, though, what we've got going on here, the xy switcheroo is still the same. Thankfully, our vertices and our foci are going to be built the same as we did with our ellipses. We have to watch out for the relationship between the A's, B's, and C's. The hyperbola relationship is different from the ellipse relationship. So we got to make sure about that. And again, going back to that equation that we bring back to the top one more time to comment here. Our standard form, x stuff over a number, our y stuff over a number, we've got to have the equals 1. Whatever is positive is going to control my orientation, and whatever is positive means my denominator is that a squared number. So that's how we are getting started with things and putting all that stuff together.